next presentation is by Hanna, who will continue our journey into the world of real molecules and chemical reactions, and she will tell about the catalytic reduction of hydrogen.
Yeah, like Dimitri said, I'm going to talk about the catalytic reduction of a proton into hydrogen gas for fuel purposes. Before I talk about my reaction, I just want to talk about hydrogen as a fuel source and some of its advantages and disadvantages. The reaction I've shown is the combustion of hydrogen gas with oxygen gas. And us chemists can clearly see the difference between most combustion reactions we think of, and that's that carbon dioxide is not produced. And that leads me to my first advantage, is that hydrogen fuel source is a clean source of fuel because it doesn't produce carbon dioxide like most fuel sources we traditionally use. We have an abundance of hydrogen in our universe. It is the most abundant element in our universe. Hydrogen gas is a much more efficient source of fuel than what we traditionally use, and it's much quieter than traditional combustion engines. There are some disadvantages to using hydrogen as a fuel, that it is highly flammable and has a tendency to ignite at very low temperatures, and has a very low viscosity, which basically means that it can leak very easily in a container through small cracks. And with the low viscosity, that also means it can fill up a room very quickly. So those two disadvantages can be a very bad combination. So strict safety procedures need to be followed when working with hydrogen. And I talked about there being an abundance of hydrogen, but hydrogen gas is very rarely found in the air because it's lighter than the air, so it's up above in our atmosphere. So instead of trying to obtain this hydrogen gas somehow, we can create it, and that leads me to my experiment. So I focused on the reduction of a proton into molecular hydrogen using a platinum catalyst, and this is the reaction right here that I used. What is formed, the intermediate of the platinum catalyst, is this platinum cluster here. And actually, like, you can see it right here, and it's centered with one platinum, and then platinums all along the sides, and hydrogens bonded on the outside. And heat is used to cleave the hydrogens from this platinum cluster. And I think it was about 2000 Kelvin it needed to be. And you can see here, like, the hydrogens are starting to get closer together, and then after time, they start to dissociate from the platinum catalyst. And this catalyst is a heterogeneous catalyst, just meaning that it's in a different state than the molecule that it's catalyzing. And so my first challenge was just modeling this in MATLAB, the activation energy, and I did this based off data provided to me by Dr. Hahn. He had only provided me with 17 points of data, so I actually interpolated it into 97 points. And this here you can see is the activation energy for the breaking of the platinum hydrogen bond. And I used the wave packet code in MATLAB for this, and one of the major changes I made was it was set up for that of an electron, and the mass was just 1. And so I changed it to about 1837 because the mass of a proton is about that much more than that times the mass of an electron. And then I ran this code at various momentums. I had a hard time getting it to look nice with positive momentum values, so the videos I'm going to show are all with negative momentum values. So this first video just kind of shows the reaction not proceeding, nothing's really happening because the momentum's too low, or not low enough because I'm using negative values. And then that was about -6, the one where it didn't really go. And then this is about a -12. And it kind of just starts to go over and then goes back and kind of does some weird stuff. But then the lower or higher, more negative I made it, this just started to be higher in general, almost above it, so then it's definitely going to go. And then you can see it just definitely goes over now because the momentum is much higher. And yeah, that is all I have.
Okay, good. Thank Hanna.